Hi, my name is Olivier Tremois. I'm technical marketing for the AI engine tools at Xilinx. In this video, I'm gonna walk you through the methodology to vectorize an algorithm for the AI engine. For that purpose, I will take the example of a fur filter. To follow this video in the best conditions, it is preferable that you have a basic knowledge about the AI engine architecture, typically the fixed point pipeline and SIMD capabilities. The AI engine programming environment is also important to understand why some tools are used and how the programs are written. Finally, and perhaps the most important, you should know what is an intrinsic and how to get information about them. The goal of this video is to program and optimize the implementation of a 47-tap symmetric filter. The data and coefficients are both 16-bit integers. In the AI engine, we implement correlations and not convolutions. It means that you have to reverse the order of the coefficients. As the filter is symmetric and with an odd number of taps, the computation can be optimized by using a pre-addition before the multiplication, except for the center tap. The first step in the methodology is to find what are the intrinsics that are suitable for your program. I have already opened the document navigator, which is here. And in this document navigator, you can find the UG 1078, which is a link to the Virtual ACAP AI engine intrinsics. So you click here, and then you have a browser opening on the AI engine intrinsics. So our filter has 47 taps. It's symmetric, and we are interested in Mac intrinsics. So if we go to the Mac intrinsics here, it's concerning multiplications and not self-multiplications, advanced for integer type. And as we have a center tap, we would like to see vector max with partial pre-adding. So if we click here, we are interested in 16-bit by 16 bits. Let's go here. And here we see that we have 16-bit complex by 16-bit complex, complex by real, real by complex. But in our case, we have real by real. So there is no intrinsic with real by real 16-bit with a center tap. So we need to fall back on a partial pre-adding, but without the center tap. So we will see this vector map with pre-adding here. If we go to 16-bit here, we have the 16-bit by 16-bit real here. And if we click, we have all the Mac symmetric. We have Mac 16, which means that it is 16 lanes computations. We have the 8-lane computation for the Mac, for the multiply subtract here, MSC. You also have the mul 8, mul 16. You also have the neg mul. So the two operations which are interesting for us are the mul 8, mul 16, Mac 8 and Mac 16. If we dig a little more, we can see that, so let's go to the 16 lanes, for example. So for the Mac 16, so we'll have V16 AC48, okay. We have a version with XBuff on 64 elements and a ZBuff on 16 elements. We also have a version on 32 elements for XBuff. And the last one is a version where you have 32 elements for XBuff plus another buffer with the 32 elements, which is the YBuff. Okay, and for the V8, for the Mac 8 symmetric, also you have the same three possibilities: 64 element for XBuff and 16 for ZBuff, 32 element for XBuff and 16 for ZBuff, and finally 32 elements for XBuff, 32 elements for YBuff, and 16 elements for ZBuff. So always 16 elements for ZBuff and for XBuff, either 64 elements or 32 elements. So now we have to choose in between 8 or 16 lanes for the mul and mak operations. The difference will be mainly in the number of data that you will have to use at each compute stage and the number of data that you will have to load. For example, here on 8-lane computation, for y0 you need d0 to d3. For y1 you need d1 to d4, so you will reuse d1, d2 and d3. So the maximum number of data that you will have to use is from d0 to d10, so 11 elements. On the 16-lane case, you will use d0 to d16, so 17 elements. So the choice is between 11 data or 17. The interesting part is that with 11 data, you fit exactly within the 256-bit section of a register. So as you don't use too many sections of the register, you can update some part of it. So you have much more flexibility to schedule read and write data operations. As I said also, you have the version with 32 elements or 64 elements for XBUF. And so it means that you can use either 512-bit or 1024-bit registers to store XBUF. There is no version of the Mac 8 and mul 8 with _CT, so center tap. So you will have to use the standard symmetric intrinsic. So the only way you can do it without problem is to divide the center tap by 2 and then use the standard operation here, making sure that for C23 here you have twice the same index here, n plus k and n plus 46 minus k. So, and then it will do, you will do this operation, C23 divided by 2, and then you add twice the same data, so it will give the good result at the end. The second step is to schedule all the operations, the mul and the mak that you have to perform, and the best way is to use a spreadsheet software. So let's start with your preferred spreadsheet software. The first thing that you have to specify is the size of the register that you will use. Here it is a 1024-bit register, that's why I have these 4 sections of 256 bits, each one handling 16 data of 16 bit each. The first section handles data 0, data 1, data 2, etc. When you will connect your filter to a previous kernel, you will have to define a margin. As you have 47 taps, you need a margin of at least 46 samples. I will choose 48 samples. That's why for the first filter compute, I have to align these last coefficients here to the first new data in the register, which is the 48th one. This graph means that the coefficient C0 here to C23 here and then back to C0 should be multiplied with the data that they are on the same column, so C0 with the data 2, C1 with the data 3, etc., etc. So more precisely, the data 2 should be added with data 48, and then the result of the addition should be multiplied by coefficient 0. Then data 3 here on the left, plus data 7 here on the right, should be pre-added and then multiplied by coefficient 1 and accumulated with the previous result, and so on for all the coefficients. As you can see, I have different colors for each group of 4 coefficients. In the 16-bit real by 16-bit real multiplications, the AI engine can perform 32 operations per clock cycle. So in the 8-lane case, it can perform 4 operations per lane. That's why I have these groups of 4 coefficients, 0 to 1 to 3, 4 to 7, 8 to 11, etc., etc. The graph you see here is for the first lane. You just have to copy here all these coefficients and paste the result, but shifted by one data to have the operation that you must perform for the second lane. If you continue like this, you have this complete graph of all the operations, and you can see that actually I can compute 16 outputs with the same data in the register. Okay, so one set of operations to compute the first 8 lanes, and then another set of operations to compute the next 8 lanes. In this view, I have separated the 6 groups of coefficients that will serve as the basis of the 6 intrinsics code that I will have to perform. The first group has been replicated below and copy-pasted in order to have a better view of all the operations that will be performed by the first intrinsic call. In the following spreadsheet views, this extended graphics will be summarized in the below stylized graphics here. In this tab, I separated the various intrinsics calls. This is a very simple scheduling where I start by loading the registers with the necessary data. You can see that I start by loading the data belonging to the margin. The first 3 256-bit sections are loaded with the margin data from -48 here up to -1 here. Then the last load is the first one that concerns new data. The first mul8, row 13 to 15 here, is aligned on the right with the new data 0 to 7. The following 5 Mach8 are placed relatively to this first mul8. C0 here is placed on index data 2. Coefficient 4 here is placed on data 6. Coefficient 8 is placed on data 10, and so on. There is a second set of intrinsics to compute the next 8 outputs. As the C0 of the last lane of the first set of mul8 Mach8 is aligned to D9 here, then the first mul8 of the new set of intrinsics, the C0 is aligned to D10 here. The graphical representation of the following Mach8 are positioned relatively to this first mul8. On the second iteration, the register is reloaded so that the next new 16 data are located on the last 256-bit section of the register here, from 16 to 31. The same intrinsic scheduling is used so that the coefficient 0 of the first lane on the right is aligned with the new data D16 here. Now that we know which operations we want to perform and which intrinsics we will use, we can go to the documentation to determine what are the values of the different parameters. We will take the example of the Mach8 sim, the mul8 sim being exactly the same except the first parameter, which is the incoming accumulator in the Mach8. In the documentation here, you can see that xbuff is the data buffer containing 64 times 16-bit integers. Xstart is an offset applied to all lanes. The granularity of xbuff being 32 bits, xstart is limited to a multiple of 2. Xstart always designate an even index of xbuff. Xoffsets is an offset specified for each lane with some subtleties that will be explained further. X step is also subject to this multiple of 2 restrictions for XBuff in the 16-bit case. X square is a second-order selection, also called mini-permute, to obtain a fine-grained selection within the buffer XBuff. Y start and Y square are the Y counterpart of the previous parameters for X. For Z, the granularity is 16 bits, so it follows the general scheme for the selection. If we want more details, we can click on this 16-bit by 16-bit scheme here. And then we have here the 16-bit by 16-bit data scheme selection. The offset for the even rows are the provided offsets multiplied by 2. For the odd rows, this is a little more complex. This is the offset of the previous even row multiplied by 2, plus 2, plus the current offset multiplied by 2. The provided X step here is given for the even columns, the odd columns being deduced by adding 1 to the step of the previous even column. The graphical representation of the first intrinsic operation is copied from the spreadsheet. It represents the following operations on 8 lanes. Y0 is equal to D2 plus D48 multiplied by C0 plus D3 plus D47 multiplied by C1, etc. And on lane 2, Y1 is equal to C0 multiplied by D3 plus D49 plus C1 multiplied by D4 plus D48, and so on for all the remaining lines. The index selection tables for X and Y are the following: 2, 3, 4, 5, and 48, 47, 46, 45 for lane 0, 3, 4, 5, 6, and 49, 48, 47, 46 for lane 1, etc. We will determine the selection parameter using the first 2x2 cells of both tables. Because of the 32-bit granularity restriction, X start and Y start should be an even number. The table for the X selection is this. You see that the selection should include 2, 3, and 4. With X start equals 2, I will select 2, 3, 4, and 5. The table for Y selection is this. The selection should include 47, 48, 49. Here I must use Y start is equal to 46 because it will select the data 46 to 49. From even column to even column, the step is 2, so X step is equal to 2. For the X offsets parameter, the even offsets are 0, 1, 2, 3, and odd additional offsets are all zeros. In Python, MATLAB, or even Excel, you can reprogram the index selection scheme that we discovered in the documentation. In this video, I created a small Python script for the 16-bit by 16-bit scheme. You can recognize it in the first level selection section of the code here. For the first run, I select the already defined parameters, but for X square and Y square, I choose a value that do not change the first order selection. I run the script for these parameters, and I look only at the first 2 tables, which is the result of the first order selection. We will determine the values of X square and Y square thanks to the first 2x2 index selection, 2, 3, 4, 5, and 46, 47, 48, 49. So we have this first order selection that we want to change into the correct order for the computation. For X square and Y square, the numbering is from left to right and top to bottom. The X mini-permute matrix is the following: 0, 1, 1, and 2 from LSB to MSB. So x squared is equal to 0x2110. Same kind of reordering has to take place for the Y mini-permute matrix. So the result here is 2, 1, 3, 2 from LSB to MSB. So Y squared is equal to 0x2312. Using these two parameters for x squared and y squared, the following selection matrices are obtained for x and y. 2, 3, 4, 5, and 48, 47, 46, 45. 3, 4, 5, 6, and 49, 48, 47, 46. This seems to be correct if we compare to what was expected. 2, 3, 4, 5 here, 48, 47, 46, 45, and 3, 4, 5, 6, followed by 49, 48, 47, and 46. Let's now have a look to the resulting code in Vitis IDE. The graph itself is a single kernel called K with one input and one output. The input window is set to have a margin of 48 samples as defined in the system-settings.h file. The window length itself is 1024 samples. The kernel code is very simple and reflects exactly the scheduling that we defined earlier. I defined the filter and input-output test vectors in MATLAB. As explained earlier, the center tap should be divided by 2 so that we can use mul8sim and mac8sim intrinsics all along. The coefficients must be stored in a v16 int16 variable, which is a 256-bit register. As we have 24 taps, we need 2 of these registers to store all the coefficients. Then we declare the data buffer and the accumulator. All the following intrinsic parameters are constants throughout the program. That's why they are declared once for all at the beginning. X squared, y squared, x offset, etc. The inner loop is separated in 3 parts. The data loading, here. Then all the intrinsics to compute the first 8 outputs. And then all the intrinsics to compute the next 8 outputs. The only parameters which change from one mul8 mac8 call to the other are the x start and y start. As you can see here, the 2, 3, 6, 10, 14, 18, and here 46, 42, 38, etc. Debugging of the kernel should be done under emulation software build configuration to get fast compilation and fast simulation. Then we can run and compare the produced output and the reference one. Output here and the reference output here. In this case, everything is correct. A new compilation under Emulation AIE configuration allows us to check the optimization of the produced code. Let's open the assembly code and search for FUR47. The inner loop is delimited by the 2 labels ZLS and ZLE, which means 0 overhead loop start and 0 overhead loop end. So here is the ZLS. And the ZLE is just here. In between these 2 instructions, you have 15 instructions, which means 15 clock cycles as there is no branching. There are 12 vector operations here, Vmax and Vmols on the right. The other ones are wait states due to the data transfers that occurred earlier. You see these three instructions here. There are no vector operations on the same line here. An optimized code should have only 12 instructions in between these two labels. Let's go back to the spreadsheet to optimize the scheduling. The goal is to interleave data transfers and vector mark instructions so that all these operations can be scheduled at the same time and avoid any wait state due to the grouping of flowed instructions. In a filter, the order in which you perform the MAC is not important. We can start with the inner taps and finish with the outer one. In this basic scheduling, the first two MACs use all the four 256-bit sections of the register. The last two ones use only two of these sections. In the second set of intrinsics, we can see that the first two instructions use only three of the four sections. The one that is not used can be changed without any problem. In the Optimize the Scheduling tab, we can reorder the two sets of intrinsics and interleave the data loading. Before the inner loop, a section of the register is prepared. We will need to be in the same configuration at the end of the iteration with a new set of data at this position. The first instruction of the loop is another load, so that the next two instructions can be done with all the necessary data. Then another load is done to perform the next two MACs. Finally, a last load is done to allow the execution of the remaining MACs. As we know that the third 256-bit section of the register won't be used in the last two MACs, it can be updated to prepare the second iteration, which starts with the same instructions as the first one. One load, two MACs, etc. Going back to the Vitis IDE, we can write the new code and compile under Emulation AIE configuration. As you can see, there is a register update before the loop, and all the load and MAC intrinsics are interleaved as specified in the spreadsheet. Opening the assembly code, we can verify that there is no more any wait state. All lines of the inner loop is filled with a vector MAC. In parallel, you also have the four loads and the two stores. Here the loads here, VLDA, and the two stores, vStore and vStore here, which are distributed throughout the inner loop instructions. Thanks for watching this video about algorithm vectorization for the AI engine applied to a fur filter. See you soon in another video related to AI engine tools and methodology. Bye.